It's one thing to listen to doom and gloom about food and fertilizer shortages, skyrocketing prices, the cost of living, or your job being outsourced overseas or eliminated due to automation. It's quite another thing to hear practical, immediately actionable advice from experts who can help you reduce the fear, anxiety, and burden of these problems. Tune in now to the Surviving Hard Times podcast from the Finding Genius Foundation with Richard Jacobs. Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out, and I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now to our guest. Hello, this is Richard Jacobs with the Surviving Hard Times podcast, sponsored by the Finding Genius Foundation.
My guest is Professor Ramani Narayan. He's a University Distinguished Professor at Michigan State University, MSU. We're going to talk about his work with fungus and bacteria that are able to consume and alter plastic waste, which will be very, very promising. So welcome, Ramani. Thank you for coming.
Thank you.
Yeah. Tell me a bit about your background. Your degree is, I guess, you're in chemical engineering, but how did you come to work on, the systems you're working on today with fungus and bacteria?
Yes. So my background is a chemical engineer, and I joined MSU in '89. And even at that time, plastics waste was a major issue. And what happens to the waste after it enters the environment, particularly because these were ubiquitous and persistent, non-biodegradable, and accumulating. So the question was, can we design new polymer molecules that could be biodegraded? And by the term biodegraded, I mean that microorganisms, whether they are bacteria, fungi, are capable of utilizing these polymer molecules when they are exposed to it.
Are you trying to create novel molecules or put additional functional groups on them? Or are you trying to figure out the existing plastics in the environment? How can they be consumed?
So originally, the idea was that if you took existing, what I call carbon-carbon backbone polymers, the carbon-hydrogen polymer molecules, which we use today in large quantities. In fact, 90% of all packaging is based on these carbon-carbon backbone hydrocarbon plastics. They are the ones which are not biodegradable, persistent, and accumulate in the oceans and land. And this is what we are hearing in terms of the stories we hear about this. So it would have been an ideal choice that we create microbes or enzymes or fungi that can break these carbon-carbon bonds and consume it and remove it from the environment. But unfortunately, these molecules, these current hydrocarbon plastic molecules, are not been around for a long time. So the microbes have not acclimatized to it and are not capable of breaking it down. And two, they are large molecules, and therefore they cannot enter into the cell of the microbes. So if microbes have to utilize carbon, and they utilize carbon not because they want to clean up the environment for you, they utilize carbon as food, fuel for their life processes. Very similar to we eat food for our life process. So that's what microbes do. And they use The microbes want carbon food, so they need carbon molecules. Unfortunately, the plastics packaging that we designed and is so ubiquitous and found everywhere is not capable of breaking down small enough to be used up or utilized by microbes as food. So that's where the problem started.
What kind of bonds can microbes break? Like carbon-carbons, single bonds, double bonds, carbon-oxygen bonds, hydrogen bonds, like which ones are...
For life, you need oxygen. For water, right? I mean, that's basic. So if you were to redesign those carbon-carbon backbone bonds with esters is got an oxygen within that backbone. So if you can use what we call polyesters, and then there is a lot more probability of it being hydrolyzed and create small molecules that are then easy to be utilized by microorganisms. And the other interesting fact is there are enzymes like esterases that are capable of breaking these ester bonds present in a molecule.
Have you seen bacteria that are able to survive in high or low pH environments? And I imagine them getting in the proximity of a potential food source, excreting something and changing the pH, the ambient pH that may, allow them to get at the molecule, get at some of the bonds, maybe cause partial oxidation or some bond breaking initially. Do you see any bacteria employing a strategy like that?
Yes, there's significant, I would say there are a lot of publications in the literature where microbes are known to grow on such hydrocarbon molecules. Or you can look at enzymes that are capable of breaking these bonds. Remember that before it can be utilized as food, it must get inside the cell. And in order to get inside the cell, not only must the molecular weight be reduced significantly, but it should also have the right hydrophobic, hydrophilic balance so that it can transport into the cell. So those are the two things. But herein where the problem comes up, what happens, why this is not taken off as this podcast says, is that the microbes, obviously, to consume those carbon-carbon molecules, they can consume, say, break it up into some small pieces and then utilize a few moles of the carbon for its life processes. But in the environment, there are all sorts of carbon sources available. So the microbes are going to go after the ones which is the most easily accessible. It is like if you are given food, if you're presented food which, you kind of don't like, and there's an appetizing another kind of food, you would eat the one which you like, not the one which you don't like. Broccoli is something you may not like. So if you're presented with something else, obviously you're going to eat that first. So in the real environment, just because it is capable of utilizing it, how quickly will it utilize it and at what rate becomes issues in this case.
Are bacteria like kids? They eat the dessert first, whatever is most amenable, they'll gorge themselves and ignore the other stuff. Or like if they're faced with two types of sustenance, like two different bonds to break in a material, will they pick the less energetic one that's easier to do always? Or like what's their behavior like when faced with food choices?
It will take the most easy to break down and digest sugar, right? I mean, all carbohydrates are sugar molecules, sugar chain molecules. And so sugar is easily utilizable carbon substrate, not hydrocarbon type plastic molecules, which are very water repellent. And so, doesn't break down that readily. So yes, the more readily available substrates going to be utilized by the microbes in the environment before they go after other hard to assimilate microorganisms, and maybe some of them they can't assimilate at all, like the carbon-carbon backbone polymers, which is why it persists so long in the environment.
In the commercial manufacture of various plastics, they add, from what I understand, thousands of chemicals So wouldn't that create void spaces in the lattice or breaks? And you might have like little islands or like nucleation sites of a pigment or a plasticizer or some other kind of chemical. And as a plastic wears in the environment, I would think those void spaces or dislocations would be uncovered, from the wearing away of the plastic and make it more amenable for bacteria to consume it. It's like in the lab, do you try to approximate outside conditions and have a plastic but like tear it up a bit or rip it apart or, deform it somewhat so that, there's places for the bacteria to gain a toehold or a foothold and breaking something down?
Yes. So in nature, that does not happen so readily, right?
Like let's say a plastic bag laying on the beach, ultraviolet light would break some of the bonds and release things, and the mechanical wear and tear of the water and, things would abrade and, I don't know, surfaces would get exposed.
Sure, I would think. Sure. And that happens. And that's where you get this whole issue of microplastics and nanoparticles. So yeah, physical processes like what you just described, UV, heat, water, they do break it down. And therefore, larger plastics like that bag becomes the source for smaller and smaller particles. And of course, as you've heard all over in newsprint and everywhere, microplastics is a big issue. It's all over the place. It's transported. The reason is that these smaller and smaller particles are not yet or not readily assimilated by the microbes. They're still there and they continue to persist, and the rate. So ultimately it becomes rate. The rate at which this will be broken down and utilized is very, very slow. So that's where the lifetime of these microplastics, these broken down fragments, is so large that for practical purposes, they are persistent and accumulate in the environment.
Do microbes eat individually, or do they form biofilms? If they can get a purchase on the surface of, let's say, a given plastic, do they form biofilms, and therefore do they have like emergent abilities that come about from the composite of these billions of bacteria forming a biofilm, and then they're able to attack certain things? Like, does the state of the bacteria and how many of them there are affect its ability to decompose?
So biofilm formation is well established, well known. That's how microbes adhere or attach to surfaces. They secrete they attach and form these biofilms, which will give them the attachment, and that's what you're looking at. But herein where the issue comes up. Just because something forms a biofilm doesn't mean that it is going to consume that carbon of that source as its food, as its, For example, biofilms are formed even on metal, on surfaces. You go look around, there are biofilms everywhere. Now, biofilms is necessary for the microbes to survive, to attach, but that does not mean that the microbes are breaking down that substrate, and after some period of time, all of that carbon will be consumed, and therefore there will be nothing left. This is, I think, where some of the confusion arises, because there's a lot of statements in the literature saying, oh, I have formed biofilm formation. The particle sizes become small. It's easy to, smaller and smaller particles. So larger area, surface area means more biodegradation. But they are degradation, they are fragmentation. They go smaller and smaller. And yes, ultimately at some point they will start to biodegrade. But that's a rate issue. And that's where these approaches of microbes and fungi breaking down carbon-carbon backbone polymers has not really done the job. It's problematic. So yes, you need to make that happen. And the way you do that then is to change the molecular structure. In other words, what I'm saying is that in the plastics molecule space, doing business as usual, which says, I'm not going to change anything on my structure, but I'm going to look for microbes. I'm going to grow new microbes, or I'm going to find new additives that's going to break it down. That by itself has not proven at all today.
This may be a very difficult question. How do bacteria know whether they can break a bond or not? Are they sensing the attractive strength of a bond, and they somehow were able to gauge, no, I can't break this bond, it would take too much energy? Like, has anyone studied this? Like, how do they evaluate the bacteria, where to break a bond and how?
Well, that's two different things, right? One, the question you're asking is, how do they know they're going to break a bond and then consume it? That is not the major driver as to how microbes utilize carbon, right? There are enough molecules and small molecules that enter inside the cell. When they are inside the cell, then they are biologically oxidized to CO2. It releases energy, and that energy released is then harnessed for its life cycle. For example, if we eat, you can eat all sorts of things. Fiber, it's not going to get broken down. It goes through the bodies, and it is good. Carbohydrates, much readily broken down, and then that builds fat and all. Some molecules don't break down fast enough. So the environment dictates how fast a larger molecule is broken down to small so that it can go inside the cell. And that's when the utilization happens. So yes, it is true that microbes do release enzymes that break down polymer molecules. But this breakdown of polymer molecules is evolved over time. So cellulose, starch, these are the carbohydrate molecules. There are enzymes that are capable of breaking those bonds, and then they are transported inside the cell. For hydrocarbon plastics, the newer generation of molecules, the enzymes, the microbes, cellular machinery has not progressed enough to be able to generate enzymes to break it down. Maybe 1,000 years from now, they would have done that. But now they are not capable of breaking down at a rate and time scale to quickly pull it into their cells and then oxidize it. But it's a great question. I mean, I think it's very important to differentiate between certain molecules like cellulose, starches, carbohydrates, which have been present for a very long time, and the microbes have acclimatized and understand it and have developed their cellular machinery to secrete enzymes to break that down and take it inside the cell. And researchers actually have those enzymes and study the rates and timescales of how that happens.
Is size like a very, very, like, could you break up certain compounds into small enough size that they would be taken up by a bacteria preferentially, but they're indigestible? Like, does the discernment of, is this food or not food, happen once material's inside a bacteria, once it's, taking it in, or does it happen before that?
No, it's inside. It decides, it will go into that pathway of how it utilizes carbon. So very similar to us. We can eat anything, right? But the body is not going to be able to break down anything we eat and convert it to energy for our life processes.
So bacteria, they'll eat anything as long as it's the right size and geometry, and then they go, oh, it's food or not. They'll spit it back out or not?
Correct. Or they'll die, right?
Or it'll kill them,
Yeah, they are not enough. And this you have seen, like if you go to the macro level, you have heard about birds' stomach being filled with small plastics. Pictures have taken of it, right? How does that happen? Well, the small pellets, which are these hydrocarbon polymer plastics, like you said, biofilm formation happens, microbes attach to it. The birds look at it as food, so they consume it. But then that little pellet their system, their cellular machinery cannot break it down. So your bird's stomach is filled with it. Now it can't eat, and it starves to death. That is the primary mechanism of how that happens. And it's very similar. Like if you take cows, theirs is a ruminant stomach. Now cows, as you know, can break down cellulose readily. So you feed it grass, hay, but we can't break down cellulose. So if you have cellulose, the fiber, it just goes through our system and we excrete it out. It helps the roughage that goes through, but it can't break it down. So it's not used up as energy for our life process. Same way, microbes, molecules can get inside the cell, and if it is used up, yes, it generates energy, it multiplies, it grows. They're very ubiquitous, so they continue to multiply and grow. But if there is no other carbon source, then it becomes dormant. And eventually, in the absence of any carbon food, it would be it would die.
Okay. So is your idea to dope plastics with certain compounds that'll make it more amenable for the bacteria to consume them and break them up? What's the strategy here?
So the strategy is exactly that change the backbone polymer so that we make it more labile, more easy to break down under environmental conditions. So if that ester, for example, we talked about replacing the carbon-carbon backbone with ester backbones. Now esters are easy to hydrolyze. So if there's enough water, it will hydrolyze it. It will become smaller and smaller molecules. It has the right groups and microbes can transport it into their cells. They then enter what is called as the TCA cycle. They are oxidized, which releases energy, which is then harnessed by the microbes for its life process. So that's how we're talking about doing it. And we validate this. So, this is the hypothesis that let's change it. Let's then expose this to a compost or soil matrix, which is teeming with microbes. And then if that carbon substrate, the molecule you have created, is a food for the microorganisms, then it must break down, it must go inside the cell. The cells will oxidize it to CO2, which is then liberated, and then the microbes continue to grow. So the test method to validate whether the microbes are utilizing your polymer molecule is by looking at how much of that carbon is converted to CO2 in a practical time frame. Then that will tell you whether the redesign of the molecule is successful or not.
What's the hardest bond to break, like a single carbon-carbon bond?
The hardest bond to break is the carbon-carbon single bond, or any carbon-carbon bond is difficult to break down under typical environmental conditions.
Well, what about, crude oil that's spilled, the oil? You've got hexane, octane, nonane, you got all these, ethane.
So there are, if you look at those oil spills and all, they're not being biodegraded as fast as, say, if you spill sugar on that same surface, or you spill paper, then you'll never see them there, right? They break down much faster, quicker, and then they're consumed. So the one messaging which I would leave it, there's no black and white area. Yes, it will biodegrade. No, it will not biodegrade, right? This is the two extremes. Depending on the availability and the ability of that molecule to break down and release carbon molecules that can enter inside the cell of a microbe, that's what dictates whether it is going to be removed or not. The microbes don't do it to clean up the environment. They do it because they need food. And that's where the rate of how fast that happens, how quickly it happens, is dictated by the environment in which it is in. For example, I'll give you a very classic example of temperature. Temperature plays a big role in this, right? You take a loaf of bread, you put it on your countertop, you take the same loaf of bread, put it in your refrigerator and then in the freezer, and you observe which is going to mold, biodegrade fast. That would be on the countertop, right? Because the temperature is 23, 25 degrees Celsius. The temperature in the refrigerator is maybe 4 degrees. In the freezer is 0 degrees. So it may not break at all. So if you look at the ocean temperatures, if the temperature of the water is 25, 30 degrees, balmy, like in the beaches and where it's hot, yes, these polymers may break down faster. But that same polymer, if it went into the Arctic or the Antarctic and the temperatures dropped to 4 degrees, it's not going to break down at the same rate and scale at which this happens in the other temperature zone. So temperature plays a big role in this microbial biodegradation process.
Why not have a series of microbes? Why not have ones that preferentially can break down some of the initial carbon bonds, and then they'll put those into a state that's now, edible by other microbes? So maybe you have to not only add multiple kinds of microbes, but also maybe some sugar in the mix to maybe get the initial ones of certain ones started so they could break it down so other microbes could then finish consuming it, just like maybe in our guts,
So two problems with that scenario, right? let's say you have a sugar and polyethylene, and this has been proposed, sort of, right? I have an additive which is going to attract microbes, and therefore it will secrete enzymes and other things, and it creates holes, and then therefore it will consume that carbon-carbon backbone polymer molecule. The microbes will utilize the sugar for sure, but there's no reason why it will go after that carbon-carbon backbone. A, the carbon-carbon polymer molecule is still pretty large for it to break down. And B, the sugar molecules, the larger sugar molecules will break down to smaller molecules and is easily transported in the cell, and it will utilized by the microbe. So this is I have seen pictures where they show Pac-Man gobbling up one after another. That does not happen in real life.
Well, are there microbes, though, that hang out around oil spills and preferentially do eat, or break up these single carbon-carbon bonds?
Yeah, they don't break up. Yes, that is correct. They get acclimatized to it. Over a period of time, they evolve that they can transport that hydrocarbon chain into the cells and then oxidize it and use it as a food source. Yes, this is where we went back to our first, where we discussed this, that microbes have not yet developed their cellular machinery to break down carbon-carbon backbone polymer molecules to small ones and then transport it. They have not evolved yet to do it at a rate and time scale like they have done for the oxygenated molecules like carbohydrates, sugar polymers, things like that.
So there's really no microbes that can do it. There's very few. I mean, there's ones that'll do it reluctantly, but just they do it inefficiently, or what's the state of it?
They remember that. So we need to, again, separate the two, right? The microbe's ability to utilize carbon for its life process happens inside the cell. So that molecule has to get inside the cell. That's one. Outside the cell, that molecule has to break down into small molecules, not fragment, not make smaller particles, not make microparticles or nanoparticles, but break it down in terms of its molecular level. It breaks down very small, and that it has the right morphology for it to go inside the cell. Now, microbes secrete enzymes. They attach to that surface, secrete enzymes, break it down, and then transport it in the cell, inside the cell. That's what they do with sugar molecules, carbohydrates, starches, things like that. But with a hydrocarbon polymer molecule, the one we have designed and used today, conventional carbon-carbon polymer molecule, they do not lend themselves to break down by enzymes secreted or to abiotic, UV and other degradations, so that it breaks it down to be small enough to go inside the cell. Now let's think for a minute. If you took polyethylene, which is one of the most traditional plastics used today in packaging, and you want to break it down, right? Forget biology. Let's talk about taking polyethylene and breaking it down into small molecules so that we can recycle. I mean, we're talking about PE recycling and other things. Do you know that to break that carbon-carbon polymer molecule to small molecules, it requires temperatures of 400 degrees Celsius and catalysts to break it down? We call it pyrolysis in chemical recycling, which means that the energy needed, you remember we talked about how does it break carbon-carbon. The energy needed has to come from very high temperatures and specific catalysts. And even then, it is converted into not one molecule, but it's converted to gases, which is released, liquid. These are the small molecules. And then you have residue, tar. So this is food for thought, right? For you to think about. If you're not capable of breaking down polyethylene and similar carbon-carbon backbone polymers to small molecules, which we know is an essential requirement to go inside the cell at room temperature, at ambient temperature, when we have to use very high temperatures and use catalyst systems to do that for us, how can the microbes break down these into small molecules at room temperature? And so, yes, it may start to chew on it a little bit here and there, but we're talking about complete removal will not happen. And that is where the challenge and that's where some of the misleading claims come from. It's a problematic issue. So you have to change the molecule, and there are enzymes, and you have to develop it and bring the two together to carry out that transformations.
Are these is the digestion going to occur in controlled lab environment, or does it need to occur out in the outer environment, just in the waterways and on the soil, or is it too dangerous to change conditions that way? Or could you change them locally? Let's say there's a spill. Could you treat, the heart of the spill so that at least it could be broken down faster, even if you can't treat the whole thing? Is there something you could add to the mix that's out there in the environment in a particular spot to help remediation?
So biology has been used for soil remediations, right? But one has to be very careful there then, right? If you are going to tamper with the cellular machinery, which is what the genetic modifications arise from, right? You increase its viability at higher temperatures. You make it such that it can access these molecules that are not typically accessible. Then you are playing with nature. Then you're going to release things which you have no control over. It's not in a controlled lab scale. Today, it's not like enzymes are not. So you may have, your audience may have heard about a company called Carbios in France, where they use the esterase enzyme to recycle PET to its constituent monomers. So they're using biology, enzymes, to break down the PET molecule and remove and convert it to the constituent terephthalic acid, ethylene glycol. And this is they are moving ahead with a commercialized plant also in the space, instead of using chemical catalysts. So biology and biological catalysts will be competing with chemical catalysts. Biology works at lower temperatures, more selective, and therefore gives you a much more pure products. Chemical catalysts require higher temperatures. Then you would also need to separate it. Then the issues about chemical catalysis comes up. So yes, biology will compete with the chemical catalysis. So here is an example of that happening. There are also examples of, most recently, of microbes, spores being incorporated into a redesigned polymer molecule, not polyethylene, which people say potentially you can do that too. But right now they're talking about an oxygenate molecule, so that you use it when you can, and then when you release it into the environment, or it gets released into the environment, the spores then start to work because it's exposed to the right environment and will start to biodegrade and remove it from the environment. These are all possibilities, but the one fundamental issue in all of this is these enzymes, microbes, are not capable of surviving high temperatures. So if you want to make a plastic film, you are going to blow it at 170 degrees Celsius. Well, will the enzyme survive that heat? So people are developing more what we call thermostable enzymes. But an enzyme that is stable at 70 degrees, 80 degrees, will it last? Will it survive the 150, 170 processing temperatures? So those are the issues that still needs a resolution.
What plastic is supposed to be the hardest one for anything to break down? Like, which ones appear to be impossible or impenetrable?
The hydrocarbon plastics, the carbon-carbon backbone plastics, the polyethylene, polypropylene, polystyrene, they are the most difficult to break down, even chemically. And so the concept is that some of these should be capable of being recovered from after use and recycled mechanically, chemically, and other types of approaches. Some of them, which are in conjunction with food and paper, that kind of packaging, should be redesigned to readily biodegrade in an industrial composting environment. So it's not just that you design microbes or enzymes to break anything and everything down, but you have to redesign the polymer such that it will break down much more readily in the disposal environments like composting or soil or even in ocean environments.
Why are these bonds so hard to break? Is it there's a loss of energy? Meaning if you break the bond, you have to put more energy into it than you would get out. Is that why they're so unfavorable?
Yes, the thermodynamics is not favorable to it. So
does it happen?
It doesn't. So thermodynamically, here is the simple statement on that. If people who are physical chemists and all will recognize the temperature at which let me back off. These long molecules, polyethylene, polypropylene, are made by polymerizing, carbon-carbon double bonds and making long chain molecules out of it. So ideally, what you want to do is you want to put a catalyst, heat it, and depolymerize it back to the original starting point, right? Then this is perfect recycling. But the thermodynamics is that the degradation temperature of these molecules is lower than the sealing temperature. The sealing temperature is the temperature at which the molecule will depolymerize, will unzip back to the monomer. Then you can easily move forward with it. So many of these polyethylene, polypropylene polymers are not thermally unzipped, depolymerized that readily. And that's really where the problem is in that.
Okay. So the bacteria will tend not to break bonds where the energy exchange would be unfavorable, meaning they have to put in more energy than they would get out from breaking the bond?
That is correct. But the bigger barrier is that these molecules do not break down into small molecules with the right morphology to go inside the cell. Because if they do, then they have the potential to be taken up and converted to CO2, releasing energy, and the whole cycle in the cellular machinery of the microbes can take over. So two separate things, right? The secretion of enzymes to break these bonds so that they become small enough with the right morphology to go inside the cell. And two, if the enzymes cannot be secreted, the abiotic process of UV light, sun, heat, water breaks it down to small enough molecules with the right morphology to go inside the cell. It doesn't have to be that microbes have to secrete enzymes to break the polymers down so that they can go inside the cell. That, of course, is useful. But you can also use hydrolysis or UV and other things to break it down small enough so that it goes inside the cell. So both is operating.
Okay. I think I got it. Is there any way to influence the environment in which the bacteria are in? Like, what if you make it a very high oxygen environment? Would that change them in such a way, maybe their epigenetics would change and then they would be able to consume these bonds? Or is there, other coenzymes or catalysts or anything you can put into the mix with the bacteria plus the plastic so they can decompose it easier?
I think it is the probability or the more easier way would be to change the environment to break these molecules to small enough molecular weights with the right morphology, and then the microbes can take over after that. That probability is much better and more easier. So if you have a disposal system, then this may be more workable because that you can control much easier to break it down. Right? For example, industrial composting temperatures go up to 50 to 60 degrees Celsius. So at those temperatures, if there is enough moisture, hydrolysis becomes faster. And therefore, the ones which could not break down in soil starts to break down into small enough molecules with the right morphology to enter inside the cell and be consumed and as a food for those microbes. I don't see us designing molecules, enzymes or microbes to take over the entire conversion process, like you said, break the bond, take it in. That is going to be much more difficult.
Right. I didn't ask you about fungi. I mean, they're hyphae.
Can go inside. Yes.
Are able to penetrate things, with very high pressure.
that other things are not. So what about a mixture of fungi and bacteria or fungi themselves that prepare and poke holes, in the monolith so that the bacteria can get at it?
No, so this is where it is. These are examples that have been demonstrated. But remember, we are not talking about 5%, 10% biodegradation, right? Let's assume that the fungal hyphae penetrates and it makes some holes and some molecules are dislodged, small ones, and they can go inside. We're talking about complete 90% plus of the polymer carbon being utilized by the microbes in a practical time frame defined by the disposal environment. For example, that requirement is 180 days in a composting system in lab scale, right? Where you don't give the microbes any other carbon food except your test material. In the soil, like for mulch films and all, it is in 2 years, 90% of the polymer carbon has to be converted to CO2 by microbes to be effective. These are the standards which are there in play. Now, it's not like, you can take 25 years for this to happen because these are organic carbon molecules and if they will eventually get biodegraded. But in the meanwhile, they are going to be in the soil, in the oceans, and impact all the life forms there.
Okay. Well, very good. Well, Ramani, where can people find out more about your research? Where can they go?
They can go to MSU website. They can go and look up my LinkedIn profile and just email me. I'll be happy to. That's the easiest way to reach out, and I can send publications and papers for them to read, to catch up on. My last name, Narayan, Narayan, at msu.edu.
Okay. Well, very good. Ramani, thank you so much for coming on the podcast. It's been a very interesting call. Appreciate it.
Thank you. Bye-bye.
Before you stop listening, ask yourself, what are 1 or 2 useful things you heard on this podcast that can help you overcome food and fertilizer shortages, skyrocketing prices, the cost of living, or your job being outsourced overseas or eliminated due to automation? Please like and subscribe and tell your friends and family about the Surviving Hard Times podcast. We're all going to need help now and in the near future.